Welcome back to differential equations. In this video, we're going to be going through some basic vocabulary. To be honest, not a lesson that anyone ever particularly enjoys, but unfortunately necessary before we can get into actually doing the work with differential equations. It turns out that there are a number of different ways that you can write differential equations, or a number of different types of differential equations. And being able to categorize the differential equations is very important. Just like in your basic study of algebra, you first learned how to solve linear equations, and then you learned how to solve polynomial equations, quadratic equations using the quadratic formula, and then you used that tool to go on to learn to solve rational equations, radical equations, and other types of equations from there. We need to think in the same terms with differential equations. It turns out that there are some differential equations which we can call linear. And there are some differential equations which we'll classify as nonlinear. We'll classify equations based on their order. The lower the order, the more straightforward the approach is going to be. So let me get my head out of the way and let's get into some of those basic ideas. A differential equation is any equation which relates a function to one or more of its derivatives. That's something that we've already talked about, but a good baseline to start with. In calculus, we never use the term ordinary derivative, but it is something that you are very familiar with. An ordinary derivative is the derivative of a function of one variable. Compare that to a partial derivative, which is a derivative of a function of several variables, and we get two types of derivatives that lead to two different types of differential equations. A very typical ordinary differential equation might tell us something like y double prime plus 2y prime plus 4y equals 0. A very typical partial differential equation might tell us something like u equals the negative of partial of u with respect to x minus partial of u with respect to y. Right? An ordinary differential equation uses ordinary derivatives. A partial differential equation uses partial derivatives. In this course, we're going to put most of our focus on two ordinary differential equations. First of all, because they are easier, and well, second of all, even if we were to look at partial differential equations, spoilers for the future, to solve a partial differential equation, the most common tool is to rewrite it using several ordinary differential equations. So it just is a matter of simplifying it, turning it into ordinary differential equations, and going from there. We can't really work with partial differential equations until we are very comfortable with how we work with ordinary differential equations. Right. So I'm not going to worry about classifying partial differential equations any further for you, but ordinary differential equations are worth trying to classify. Although technically this classification could apply just as nicely to a partial differential equation. The order of a differential equation is the highest order derivative which appears in the equation. So if I have an equation that looks like y prime equals 2y plus 1, well, this has the original function y, its first derivative y prime, and no other derivatives. So this is a first order equation. Y double prime minus 4 times y prime equals cosine of y. This has the function y, its derivative y prime, and then the second derivative y double prime. So this is a second order equation. We can go to higher order, but again, for the sake of simplicity, we're going to by and large stick to first order and second order equations in this course, just because there's only so much time in a semester. The other tool we can use for classifying differential equations is the idea of linear and nonlinear. In a linear differential equation, no term includes multiple functions or operations on functions, which seems like a pretty straightforward definition until you start to get into the details of things. So some of the equations that we've looked at previously, y prime equals 4y minus 1. To put everything together, this is a first order equation. This is a linear equation. If you think about it in terms of polynomials, y and y prime, if you think of those as the variables in a polynomial, you have a linear polynomial. And that's one way of thinking about the fact that we have a linear differential equation here. So this is first order, it's linear, it's ordinary, first order linear ODE. Right. We can have, of course, a second order linear ODE. and we could have higher order linear ODEs. One thing that has not come up in the examples that I've given you so far is that a differential equation is allowed to also include the independent variable. So if we're working with our function y, and let's give it an argument. We could write this as y of x, or we could write it as y of t. I mentioned in the earlier videos, sometimes we're going to be dealing with things that are spatially oriented, in which case I'll be talking about y as a function of x. But most of the time we're going to be thinking about equations that are oriented in time. So y as a function of t is going to make a lot more sense. Right? So if I have y prime equals 4y minus 5t, this is still a first order linear ODE. I don't think there's any real arguments on that one. It's the next one that starts to cause some confusion. If I have y prime equals 4y minus 5t squared, if you're anything like me, as soon as you see that squared show up there, your brain immediately starts thinking about the fact that, well, when it comes to polynomials, if you have something squared, it's no longer a linear polynomial. And that's absolutely true, but it doesn't matter in this case because my definition of linear talked about the function and its derivatives, not the independent variable. I don't care what the independent variable is doing. In terms of the analogy to a polynomial, anything that has the independent variable in it, I can treat as though that was a constant coefficient, and things will still work out surprisingly well. So in this case, even though I've got a t squared, this is still a first order linear ODE. And if instead of having the t squared on a term by itself, if I had that being multiplied by the y prime, this is still a first order ODE, right? So I don't care what the independent variable is doing, it's still linear if everything else behaves nicely. The only way to make things nonlinear is to have mess happening with the function or its derivatives. Right? So if I have y times y prime is equal to t, now this is nonlinear because taking two functions, y and y prime, and multiplying them together goes against linearity. Likewise, if I had y prime equals 4y squared, then I would suddenly have a nonlinear first order differential equation. All right. There are a couple of other classifications that are going to come up a little bit later on in the course. We can think about whether the differential equation has the independent variable showing up or not. We can think about whether that independent variable is in a term by itself or in the coefficients of some of the function or its derivative, or possibly both. And for some of the things we do later on in the course, that's going to be important. I'm going to let it rest for right now, and just those bits of classification, ordinary or partial, first, second, or higher order, linear or nonlinear, is going to go a long way to giving us the tools we need to figure out how to solve the differential equation. Speaking of how to solve, I guess another thing that we should talk about is the solution. I guess I should write this as a solution. A solution to a differential equation is any function which satisfies the differential equation. So if I look at a fairly simple example, if I want y prime equals 5y, sorry, I forgot something in this. Nope, that didn't quite work. There we go. All right, we won't be consistent with this, but when we're looking at a particular solution, it's not uncommon to use the Greek letter phi to represent the function that we claim as a candidate solution. All right, so for the function y prime, or for the differential equation y prime equals 5y, we can ask the question, is the function phi of t equal 2e to the 5t a solution to this differential equation? Well, to figure that out, we can differentiate. We can find phi prime of t, which in this case is going to be 10e to the 5t, and we can plug that in. We have 10e to the 5t equals 5 times 2e to the 5t, and since 10 is actually equal to 5 plus 5 times 2, this works. And I can say that yes, it is a solution. Now, something you almost certainly remember from fundamental algebra coursework, when you're dealing with a linear equation in two variables, or in one variable, I guess, when you're dealing with a linear equation in one variable, there is almost always one unique solution. When you're dealing with a quadratic equation in one variable, there is almost always two unique solutions. Special cases will give you infinitely many solutions or no solutions or repeated solutions. But there's a nice rule of thumb that works there. In differential equations, that's not quite the case. One of the big ideas of the integral and the antiderivative. For any given derivative, there are infinitely many antiderivatives. There are infinitely many functions where when you take the derivative, you get to the same thing. And a consequence of that is that a differential equation by itself almost always has infinitely many solutions. So when we're looking for the solution to a differential equation, sometimes you'll see it described as looking for a family of solutions, or sometimes you'll see it described as looking for the general solution. All right, so going back to the same differential equation, y prime equals 5y. We can show that the function phi of t is equal to a times e to the 5t is a solution to this differential equation for any real constant a. And we can do that just by differentiating. The derivative of this function is 5a e to the 5t, and then plugging in, we get 5a e to the 5t on the left-hand side. On the right-hand side, we get 5 times the original function, which is a e to the 5t. Right, that was a very difficult thing to prove. All right, so now we have something to work with. We know that a differential equation is going to have infinitely many solutions. And we're generally not interested in infinitely many solutions. Differential equations almost always come out of some practical application, and we're going to have to look for how that application fits into everything. And so there are a couple of tools that we can use for that. The most common one is what's called the initial condition or the initial value problem. An initial value problem combines an nth order ordinary differential equation with n initial conditions. All right, some theory here. If you're really interested, we can prove that these things are true, but I don't find the proof to be all that interesting, so I'm just going to gloss over it. An nth order ordinary differential equation has a family of solutions with n arbitrary constants. All right, that first statement is a powerful one. And if you just take a minute to think about it, it will make sense to you. If you want to take an nth derivative and get back to the original function, you're going to perform integration. You're going to perform integration n times. And every time you perform integration, you're going to introduce an arbitrary constant. Again, there's some technicalities, there's some specifics that I'm very much hand waving across because I don't think they're all that interesting. But I hope that that picture gives you the sense of this. It should be reasonable to expect that this statement is true. And if we have n arbitrary constants, we can use a system of n equations to solve for n unknowns. That's a basic idea in linear algebra. If you've not taken a course in linear algebra, that's okay. This is one of the earliest results. It's probably something that has been mentioned in an algebra class. Whether or not you've seen a formal proof of it, it should be something that makes sense. If you have more equations than unknowns, you have what's called an overdetermined system. That's where you are very likely to get no solution because of a contradiction. If you have more unknowns than equations, you're very likely to end up with an underdetermined system where you don't have enough information to solve completely, right? Given one linear equation in two variables, there are infinitely many solutions to that equation. We plot them all on the coordinate plane and we get a straight line. If you have a system of two linear equations in two unknowns, then most of the time those two lines will intersect at a single point, and that single point is the solution to the system. That's the idea we're talking about here. But with those two ideas, we can reach the conclusion that an initial value problem usually has one unique solution. I do have to caveat usually here. Again, if anyone is going onward to study additional mathematics, you may go on to take higher level differential equations courses. In my own personal background, my second course in differential equations was all about this word usually. My third course in differential equations was all about what happens if you have many differential equations going on, which is a lot of fun. My fourth course in differential equations was all about the partial differential equations we talked about before. And yeah, I've taken a lot of courses in differential equations. There's a lot more that you can do that I haven't looked at yet. Um, and so I like to mention we are just scratching the surface of what's possible with a differential equation in this course. Much like in an algebra course, you learn some basic rules for solving equations, but how many different ways have you extended that and used it in more powerful places moving on from there? All right, but let's take a look at a specific example here. All right. So two problems here. The first one, show that the function phi of t equals a times e to the t plus b times e to the 2t is the general solution for the ordinary differential equation y double prime plus 3y prime plus 2y equals 0. That's actually the problem that I'm going to have you work on your own for this video. So you're welcome to pause the video and try that, or watch me go through the second part and then come back and show that first part on your own. But I would like you to work through that on your own at some point here. And then the second part that I will do with you is to solve the initial value problem given by that same ODE, coupled with the initial conditions, ICs, y of 0 equals 0, y prime of 0 equals 3. And with this example on the screen, I guess I can talk about why we call them initial conditions. Thinking about t as our time variable, the first thing that happens is the thing that happens when t is equal to 0. And knowing what is happening when t is equal to 0 tends to be the easiest thing in a system that is doing stuff. For example, a lot of the applications, a lot of the examples we're going to look at in this course are going to involve kinematics. If you have an object that is in motion, knowing where it is and how fast it is going when you start your observation is generally the most usable thing, right? If you are studying a tennis ball launched out of a tennis ball launcher, well, you know where the launcher is and you know how fast it's going to launch the tennis ball. So you know the starting position and the starting velocity before you put the ball in the launcher. And so that's what we have here. Y of 0 is the position at 0. Y prime of 0, remember in kinematics, the velocity is the derivative of position. So we have the initial position, the initial velocity, and we're asking to see how is this particular tennis ball going to move. Okay, this example, this differential equation really has no bearing on tennis balls, but that's okay. We can still solve it anyway. And to solve the differential equation, or to solve the initial value problem, we do first need that general solution. And we'll be talking throughout the rest of the semester on how to find those general solutions. But given a general solution, given our initial conditions, let's see, phi of t is a e to the t plus b e to the 2t. And we can differentiate to get that phi prime of t is a e to the t plus 2b e to the 2t, right? Just taking the derivative of the function that was given to us. Now that we have these things, we can evaluate when t is equal to 0. So phi of 0 is a e to the 0 plus b e to the 0, and the initial condition tells us that that should come out as 0. Phi prime of 0 is a e to the 0 plus 2b e to the 0, and the initial condition tells us that that should come out as 3. Cleaning up a little bit, we have that a plus b is equal to 0, and a plus 2b is equal to 3, and that's a system of two equations with two unknowns. And given a system of two equations and two unknowns, we should be able to solve it without too much issue. In this particular case, we can very quickly see that b is equal to the opposite of a. And so take that and plug it into the second equation gives me that a minus 2a is equal to 3, which means that minus a is equal to 3, which means that a itself is equal to negative 3. Plug that back into the equation that we had over here. B is minus a, but a is now negative 3, means that b is positive 3. Right. Once we have our general solution, very often using the general solution and the initial conditions to figure out the values of the arbitrary constants is very quick. It's always solving a system of equations. The system of equations is almost always very easy to solve. Not always, but almost always. But then we take those values, we put it back into our original function, and we get phi of t is a, which is negative 3 e to the t, plus b, which is positive 3 e to the 2t. And again, this particular equation does not at all model tennis balls being launched out of a tennis ball thrower, but the idea is still there. We have our system, we gave our setup, and the math has given us this function, which is going to model what happens to the object in question as time continues. Right. Again, I'd like you to go back and look at why this is in fact the general solution. Work through, see what you can do demonstrating that, and I'll see you in the next video.